maybe we should get started. It's a pleasure to have Jeannette with us. Jeannette did her PhD at KTH. Then, she led a group back in MPI and then joined Stanford a couple of years back, where she heads the interactive perception and the robot learning lab. So Jeannette has done a lot of work ranging in many areas of manipulation, which is truly exciting. And Jeannette's work has received many Best Paper awards and an early career faculty awards as well. And today, Jeannette is going to talk about how we can merge, two big fields of language and robot learning together. So super excited to hear more about it. Jeannette, thanks once again for coming, and Aviv, thanks for organizing. Jeannette, please take it away.
Yeah, thank you, Pulkit, for this nice introduction. Thank you for inviting. I'm really happy to be able to talk to you and also to meet some of you later on. Cool. So yeah, let's talk about these two big fields of natural language or vision and robot learning. It's actually three big fields. And so I think I would say personally that we've seen a lot of progress recently or in recent years on just low-level sensorimotor skills on robots and implementing them. And so here, I just picked two works from my own lab, but there are so many out there, of course, that are also doing great work. And this is a bit of an older work that I've done just when I got out of MPI, basically moved to Stanford, where we really implemented an entire system that combined real-time perception with reactive motion generation. And so here, this robot called Apollo was supposed to grasp this box, this chips box, this Pringles box there, without knocking over any of the stuff that is being put in its way. So it really had to react online and process all this visual information like at millisecond level to be able to do that. And so here's the other work. That was kind of my first work, I guess, that was published more or less after I moved to Stanford, where we looked at other manipulation capabilities beyond pick and graft. And specifically here, we looked at tag insertion and how vision and touch can be fused to enable a robot to learn, I would say relatively quickly, how to do an insertion task, exploiting these two modalities, even though it may not know exactly what the shape of this object is. And even though Michelle here, my student, is perturbing the sensors and the robot itself. So that's cool. So I've had a lot of fun, and I'm still having a lot of fun on looking at these low-level sensorimotor skills. But recently, I also got very interested in going beyond sensorimotor skills, just a few one of them, and enable robots to actually do tasks that require reasoning over a long horizon. And an example task in this kitchen here, for example, could be emptying the dishwasher, preparing different meals, stowing groceries, and so on. And all these kinds of tasks require to chain these kinds of basic sensorimotor skills that you've seen before together in a meaningful way. And so here is an example task. So for a robot, basically, to do that kind of long horizon task, it requires both some kind of high level, maybe symbolic reasoning and a continuous motion planning. And this is an example for the Tower of Hanoi, showing you two symbolic solutions to solve this puzzle associated with the continuous motion trajectories, basically, that a robot has to execute. So the symbolic task plan can consist of symbolic actions, such as pick and place, transport, and so on, that have to be realized by robot motion. And the challenge is really to find a valid symbolic plan that may not necessarily be kinematically possible, and therefore has to be checked by planning robot motion for the entire task plan. And this is a very expensive search. And the field of task and motion planning addresses this challenge. And so today I want to talk a bit about an entire system, a robot system for long horizon tasks. And I want to talk a little bit about the puzzle pieces that are coming in there from our lab. And I don't want to claim that we solved all of this, but we're like puzzling in all the different pieces. So so what does a robot system for such a, that can do such long horizon tasks look like? Well, I think it needs some kind of task planner that initiates a motion planner which is, and again, which is speaking or giving feedback back to the motion planner, whether this, to the symbolic planner, whether this symbolic plan is even possible or not. And so, as I said before, this is solved by task and motion planning, or TAMP here. And then the motion planner, once it's a task and motion plan is found, actually sends these trajectories down to the reactive controller that executes in an environment. And then hopefully we have some feedback that comes back from the reactive controller or to the reactive controller, so that it can react to something, potentially change the motion plan, or even change the task plan. Okay, so this kind of system, that would be wonderful to have. And of course, we also need perception for this, where the environment is perceived in some way and really feeds back whatever is necessary to each of these different stages of such a system. And so I will talk about different pieces that we inserted here in order to realize that system. And for the simplicity of the graph, I will, in the next slides, mostly leave out the explicit information flow from the perceptual system and just mention it when I specifically talk about this. But I come back to this later. Okay, so I think in order to realize that kind of system, I think there are three principles that are really important that we try to realize in such a system. So the first one is that of abstractions. So that abstractions are basically a way to filter out the relevant information for whatever layer you have in this particular robot systems. Another principle is learning from demonstration that just helps to bootstrap learning really in humans, as we know, but also in robots, it's really helpful, as we also know. But the question is, of course, always, how do you do this? And another important principle that we're trying to address or kind of implement in these kinds of systems is that or is the ability to always replan. So if something goes wrong, right, you want to just keep going and recover from this failure. So these are the three principles that I'm going to mention throughout the talk as well. So I want to start this talk by introducing task and motion planning a little bit more formally. And specifically, I want to focus on how we can enable the adaptation of the plan when the environment changes. So this work is really based on the principles of symbolic abstraction, but also we specifically wanted to have a system that can continuously replan, even if we have this really expensive search problem in task and motion planning ahead of us. Okay, so here's an example, again, for what we want to achieve. The goal of this robot is to place the small box on the larger box. And the problem is, though, that the small box is outside of the workspace. And so for the robot to find a solution that actually exploits this hook that is in its workspace, it has to really combine symbolic and geometric reasoning. And I think a really nice work that looks at this is this work by Marc Toussaint that was actually done while he was visiting MIT together with Josh Tenenbaum's lab. And so this is really a cool paradigm and framework, but we really wanted to implement a system that is actually adaptive to uncertainty. So, for example, the particular objects, they might move while the robot is actually executing the task. And the question is then, how do you adapt this plan, or how can you deal with this kind of dynamics in the scene? Okay, so let's look at trajectory optimization a little bit more generally. Trajectory optimization is basically what we use for continuous motion planning. And so here I just going to introduce a few variables. So we basically going to control as state variables x the end effector motion, and we want to find basically the minimum cost trajectory of the end effector, or we want to actually find minimum cost control commands, the motor torques, and the trajectory cost is dependent on the state. Okay, so this cost function is pretty standard, right? It consists of a terminal cost and of this running cost that takes the dynamics into account. Okay, so that's just the pretty much standard trajectory optimization problem. And so Marc Toussaint and et al. In this paper, they have used logic geometric programming, which basically combines the logic planner with a motion optimization. And what they did is to basically add discrete actions, but also discrete state. So discrete actions are called A here instead of U for the continuous control commands. And they also introduce a bunch of constraints. So for example, there's a constraint on the start, on the final state. And you see here is the S actually showing up, which is a discrete state. We have constraints provided by the continuous system dynamics, which change dependent on this discrete state here, S. So it doesn't only depend on the state of the n effector, but also of this discrete state. And then we have instantaneous system dynamics that change when the discrete action basically change. And then, of course, we have the constraints provided by the action skeleton coming from the logic planner. Okay, that does actually the task planning. So that's the kind of optimization problem that we want to optimize here. And as I mentioned, that's an expensive search. So for the logic planning, we basically use strips planning. And this is just a write-out of this planning domain for this particular task that you just seen the robot do with the hook and the box and all of this. And what this thing outputs is a planning tree where you see on the nodes, you have basically the state of the environment with all these propositions. And then the actions are on the edges. And yeah, and they basically change the state in a predefined way. Okay, cool. So, then the trajectory optimization problem in this particular paper that uses logic geometric programming and motion optimization looks something like this. It uses, it actually does trajectory optimization in joint space. And it's very nicely formulated. So the sum of these trajectory crossed across all time steps result in a banded Hessian that can be inverted efficiently using Gauss-Newton. But the constraint function, as you can see, the S path and the S switch, they actually depend on the entire trajectory in joint space. And this coupling makes the Jacobian of the constraint function really complex. And also, if the environment changes in any way, the joint space trajectory becomes actually invalid as soon as the environment changes in an unexpected way. Okay, so now what we wanted to do is to really change that. How can we make this robot be able to also adapt by still using this nice framework of task and motion planning? So given, again, an action skeleton, we want to derive a continuously valued motion plan that realizes the symbolic plan. And so our specific contribution to task and motion planning is to formulate this problem as optimizing over a sequence of relative Cartesian frames instead of joint space trajectories. And this object-centric representation has several advantages. So let's look at these examples. So you may want to pick up this green box here on the left and place it on the blue shelf that's on the right? So these are two steps in this task plan. And then you first control, so using this joint space formulation, you first control the joints of the arms such that the end effectors in a specific pose relative to the target green box, right? So you want to actually achieve this Xi1 here. And now, if you actually execute this in the real world, right, there are many ways in which this green box may end up in the hand due to noise and perception, you know, the robot doing random things as always. And so depending on how this box actually ends up in your hand, that influences how you will need to control the joints of the arm for placing then the green box on the blue box. And that is really shown here on the right side. So if you optimize the joint trajectory, which is what is most commonly done, this trajectory would need to be replanned. Now, again, this expensive thing has to be rerun. However, using our object-centric representation, we just control the box in whatever way it is in the hand relative to the blue shelf to achieve the desired relative transform Xi2. Okay, and so really, the way the box ended up in the hand doesn't matter. You just, but the requirement is you kind of are able to track the box and all the other objects. Okay, so how does this look like? Our formulation basically optimizes over relative Cartesian frames that are denoted here by psi square. And so this decouples the constraints over time, as you see here in the F path and the F switch, and it's much easier to formulate. The objective becomes more complex, as you see here. So this objective is now over the entire trajectory, not over neighboring states anymore. But the plan, the nice thing is the plan stays valid even if the objects move. And you also see that we actually control the and effector instead of the joint space. So we still need a low-level operational space controller to basically get the robot to move. But yeah, this is also pretty well understood. So this is basically what we did. So the resulting system looks like this. So we have this task planner that searches for a logic plan, basically a symbolic plan that can be executed by the robot, given all the kinematic constraints and all of this. This is the TAMP framework. And then we send this motion plan to our reactive controller, execute it, and get feedback from the environment where things actually end up. One thing we haven't yet done is to actually maybe redo this trajectory optimization of the Cartesian frames. So that is something maybe interesting for future work. Okay, so here's again this execution that you've already seen in the beginning, right? So here's the Tower of Hanoi, and there are two symbolic solutions for this. And you see that the robot has also planned all the continuous actions that are necessary to actually execute this very long horizon task correctly. And so again, the interesting thing is with that framework, these plans actually stay valid even if the objects move, right? So the robot never replans the trajectory because the Cartesian frames, they're attached to the objects. And if the object moves, the Cartesian frames move. And so the robot still knows which object it has to pick up and what orientation and so on, because all of this relative planning stays the same. Cool. So now I promised I come back a bit to perception. So of course, in simulation, we assume we have like perfect information or whatever, but we also wanted to put this on a real system. So what we did here for now was just to use a model-based object tracker from 2013 that we had before in order to basically track all these objects. And we had to actually augment it with markers because the objects were pretty small. But here's basically the system work in the real world, while Toki, the author of this work, is actually perturbing the objects and essentially being annoying to the robot. But it can still do what it's supposed to do, even if these things move. Yeah, so just to summarize this part of the work, so we developed this object centering task and motion planning in dynamic environments. And the main idea was to use symbolic planning to create an action skeleton that translates into this constrained motion optimization problem. And the algorithmic contribution was to reformulate this trajectory optimization problem to optimize relative Cartesian frames. And so we achieved task and motion planning in dynamic environments. Yeah, so this was kind of the first part of the work on the path towards having an entire system that does long horizon reasoning over many different, for many different kinds of tasks. And as I mentioned before, in this TAMP framework that I just showed you, we use trips planning to search for the symbolic action plan based on pre and post conditions of these discrete action primitives like pick, place, and push here in this particular case. Okay, and as I also mentioned, this outcome of the strip planning is basically this symbolic tree. But remember that there are three principles that we think are key to building such a robotic system: abstractions, learning from demonstrations, and keep replanning. And we want to basically keep the logic symbolic planner to provide a long horizon high level plan and trigger the correct low level sensory motor skill. But now the tricky question here becomes, what if we need to actually also adapt the task plan? What if somebody perturbs the environment in such a way that a local adaptation, what I've just shown you, is not feasible anymore, and there actually has to be a different step in the entire task plan. So the tricky question then becomes, how do we perceive the symbolic state of the environment for the many possible predicates that are now required for planning over this large variety of actions? Let's say we have like more than just like 3 action primitives now. So basically, if you want to enable this continuous task replanning, especially, we really need to basically ground the abstract symbols to enable this replanning. And so in the next part of this talk, I want to talk about this work on how we grounded predicates through actions that we just submitted to RAL and ICRA. Okay, so so basically what we're trying to do is, if you see this arrow between perception and task planning, we want a way to continuously monitor the symbolic state, not just the continuous state. And we want to do that in such a way that it's useful for many different actions that go beyond pick, place, and push. Okay, so there are, of course, lots of recent examples of work that use symbolic planning. So for example, the logic geometric programming work from Marc Toussaint et al. And all of these works require some way to perceive symbols in the environment. And perceiving symbols in the real environment is currently really an unsolved problem. Without a way to perceive symbols in the real world, all of these works are currently limited to either simulated environments where symbolic states can easily be obtained, or in simple known environments where visual heuristics for symbolic states can be somewhat coded by hand. So our work that I'm going to talk about next is really aiming at enabling these works to move from simulation to reality, or from simple to more complex setups, hopefully. And computer vision caused this problem of detecting symbolic states. Basically, they deemed this as maybe visual relationship detection or scene graph generation. And here's some sample works of this. But all of these works, actually, they rely on manually labeling data sets. And this is extremely expensive. And actually, typically, not all of the propositions are annotated densely. So here you see, unfortunately, I forgot what the example of this work is right now, but from which work it is. But on the middle, you see all the symbols that are actually labeled in this work, so the visual relationships. And on the right, the stuff that just appeared was all the things that are still true, but are not labeled in this particular image, right? Because it would just be too expensive to do this, for example, through Amazon Mechanical Turk for these masses of images. So our idea was to basically find a better way to automatically label symbolic states in images so that we can train these predicate classifiers for task planning. And our idea is specifically to exploit that we know how actions are changing with symbolic states. So let's look at this particular example where you want to put, in this particular example, an egg into a bowl. So then you know that before this action happens, the egg is basically in the hand, and the egg is not yet in the bowl, as written here. And then after this action is executed, you know that suddenly what is true now, the propositions that are true, is that the egg is in the bowl and the egg is not in the hand anymore, right? And there are also other things that are true, but basically this action put into egg bowl changes the state in this particular video of this person putting the egg in the bowl in a predefined way. And this we can exploit so that actions give automatically partial state labels for potentially many different videos. So what we need to do in order to exploit that idea is to define a symbolic domain. And I will talk about how long or not long that actually takes later. And then we acquire a data set of actions, for example, in videos. So I will show you that, like works that actually have done that. This is basically also already done for us. And then once we run the manual labeling, exploiting this idea, then we can learn visual groundings that are maybe useful for task planning. Okay, so I just want to give an overview of this particular method. So again, we are working with the planning description language domain. So we're going to define, just like what we did before in the task and motion planning framework as well. We're basically going to define a bunch of predicates, so in, closed, locked, and so on, that have different kinds of numbers of parameters. So this, for example, is a predicate, and it has these parameters. And when you instantiate the parameters, they become basically a proposition. And the state is essentially the set of all the propositions that are true. Okay, so the PDDL domain also has a bunch of actions. And these actions essentially have preconditions that are described in this way, where all of these states have to be true, and they have postconditions on what has to be true when the action has been executed. So that's like just a super brief overview of what we're using. And for our particular method, we are also going to flatten this first order logic from the preconditions that are described in this way to get collapsed what is called the disjunctive normal form that you see here. So this is just all the set of states that are actually true. And you're going to see later this, I think the paper is actually on arXiv. No, I'm not 100% sure, but just ask me in case it is not. It will be soon, for sure, if it's not yet. And there's a theorem in the paper that also this is the best we can do. I don't want to go into detail right now. Okay, so this is basically from the planning domain that we're looking at for each of the action, how the description of the pre and post condition looks like. And so then we also, like, let's say once we have our labels that we derived from this planning domain description, we can now train a predicate networks that basically classifies whether a certain predicate is true or not. And for this, we actually leverage related work that uses that actually does visual relationship detection. And so the way we train this is by using these kinds of annotated frames that we basically got by exploiting videos that are annotated with actions. So here we have like one frame that is annotated in with these kinds of, or that basically that is put into this network, and this is kind of the output that we get from it. And you see that the closer the hand comes to, or basically if you look at all of these different frames, the closer the hand comes, the output of this network also changes. This is actually looking at the hand in the particular frame instead of at the cup. And then you also have all the predicates that are looking at the relationship between the cup and the hand in this particular frame. And you also have the spatial relationships here for when you actually switch these two predicates as well. Okay, so this is what this predicate networks actually output when you feed in all of these different pieces of information. And so here's how we train this network. We assume we have a before and after image from a video in which you see an action being executed. And the network that I just showed you basically predicts the state, basically has classifies each of these predicates, as you see here. And we do have, from our automatic labeling using this insight that actions provide us these labels, we have these pre and post conditions that are true. And then we use basically cross entropy to computer loss that then trains this predicate networks for improving these predictions. Okay, so how well does this work, is I guess the question. So as a proof of concept, we apply our framework to the 20 billion something data set that is a large scale data set of 200,000 videos of humans performing 174 common manipulation actions, such as close something or push something or lift something with something. And this is a very difficult data set because there's such a wide variety of environments and contexts. And our hope is that by training predicate classifiers on this data set, we can obtain something that is useful for identifying symbolic states also in the real environment. Okay, so now let me come back to one of the main points of this work, which is that using this insight that actions actually provide these automatic labels is cheaper than manually annotating. So for this particular data set, we have 171 different actions and 151 propositions and 130K videos. So we threw out some actions that I think are just about pretending something to do and things like that. So these ones we left out. So that's why it's 171 actions. And so if we had someone actually hand labeling all of these states, as it was done in previous work, and we would assume maybe this person needs 2 minutes for the first stream and 10 minutes per video, then this would result in 200K working hours, or the equivalent of 7.5 years to actually do all this labeling. Now, if you had a grad student who knows a little bit about logic planning and the PDDL language and all of this, then maybe we can assume that this person needs 10 minutes per action, which translates to 30 working hours and maybe 4 days of work, which is quite a significant improvement. 1 sec. Sorry. So this is really just to show you that if we were able to automatically label these videos using this insight that action provide the automatic label, we would have a significant advantage in labeling effort. Okay, so here's some results that I want to show you. So this basically shows how we collect the training data. We basically sample in the videos from this 20 billion something data set a bunch of frames at the beginning of the video and a bunch of frames after. And so these are the before and after images that we use. And then we find that apologies. We find that we can basically get an F1 score in training of 0.96 and on testing of 9.2. So this is pretty good. And here are just some examples of what the predicate network actually outputs for every proposition, for every frame. Actually, we can only show not all the 151 propositions in total. It's a bit overwhelming to watch all of them. So we only show the propositions that are relevant to this particular action. So we also show when the pre and post conditions are actually defined. Is there a question actually?
Jeannette, I was just going to ask you, so like for example, over here, the action is approach, right? Mm-hmm. And I guess this doorknob is a detector which is running.
Yes. Yes.
And so the approach tells me that before the approach, I am not close to the doorknob, and finally I'm going to be close to the doorknob. So then are these scores like not close doorknob? Are these a score of the detector itself, or are these some other score?
So the detector, you mean the object detector? Yeah. So the object detector is completely independent, right? So we just assume is it YOLO? Is it COCO? Like, I think it's YOLO actually that we use here. Sorry, I don't remember which one, but we use just one off the shelf. And so that one detects, the doorknob. And I think we also have hands often in the video. So these are detected with media pipe with the hand tracker there. And so these scores that you see here of these propositions that actually take as input the doorknob, whatever is detected. These are actually the result of training this classifier network that I showed you with these automatically labeled frames.
Okay. Okay.
Thank you for the question. Any other questions since I'm at it? Not. Okay. So so you see like how this works. Here's like another example about closing something. Similar story. We just show the propositions that are actually important. And again, we use like an object detector off the shelf for detecting hand and book. But these propositions, they are trained using this relationship network that I just showed you with the automatically labeled data. Using our method of only the actions as a label. Here's also another more complex example, bending something until it breaks. So it detects the toothpick even when it breaks, which is kind of interesting. And the hand, and you see that that there are also a bunch of, that this looks very reasonable in terms of the predicates. And what is interesting here is that there are also predicates that are correctly output, although they were not directly trained on these kinds of examples, right? So broken and deformed, for example, I think the labeling here might just be on broken and not on deformed. So there are some interesting interactions where actually training on all of these different actions, someone gives you predicates that become true, even though they are not strictly defined on this action that this video is, for example, labeled with. So here's another example of poking something so that it falls over. And again, it looks, it looks all reasonable. Okay, so now we have a way to cheaply train all these predicate classifier using this insight that actions provide simple weak labels, essentially, that we can exploit. And so we have all these data to train these predicate classifier. You've just seen examples of how it works. So how do we plug it into this entire system now for the robot to actually do online task replanning? When we have these symbolic state classifiers that help us to perceive the initial state of the environment, but they also, what is interesting now is that we can run these classifiers during the entire action. And so they allow us to continuously monitor the symbolic state and trigger this replanning. So here's an example for this work where we want to basically remove all the fruit from the table. And so the goal condition is for all the fruit that are, they don't have to be on the surface, right? And everything has to be closed for whatever is closable. And so here is how this looks like for all these predicates. And you've just seen also Toki actually closing the drawer again. So the robot had to actually replan and figure out like, oh, my preconditions are not fulfilled anymore for these particular actions. So I actually have to do something else before I can continue. And here again, Toki is moving around stuff. Yeah, so what is also kind of nice here is that we trained all of these predicate classifiers on real videos. So this is not done in simulation. And therefore, we can use these predicate classifiers also directly on real data. So there's no sim to real gap in that sense to be closed, right? Because it's already real data that we trained on. Cool. Yeah, so just to summarize this work, we basically, so this work is called Grounding Predicates for Actions. I apologize that I don't know if it's already on archive, but we submitted it to RAL and ICRA a few weeks ago. And the main idea is that we exploit that we know how actions change the symbolic state. And this basically provides us a cheap way to do proposition labeling in video demonstrations by humans. And the algorithmic contribution is a framework for obtaining partial state labels for video demonstration and training these predicate classifiers. And the result is that we have 37 predicate classifiers that are relevant to 172 different actions that can be used for closed loop planning. All right, so that's pretty cool. And so now we could, for example, plug this in into this task and motion planning as well to do reactive task planning as well. Okay, so one of the things about this logic geometric programming framework that I showed you at the very beginning, though, is that we have to basically define all of these different actions in such a way that we can translate them into constraints of this particular optimization problem. And so that is really annoying. I can tell you can talk to Toki about that, how annoying this actually is and how tedious. And so it's very difficult to scale this kind of translation of these symbolic tasks into these constraints, to scale these up to potentially many different kinds of actions that we want our robot to do. So let's say these more than 170 actions that are in the something data set, for example. And so we really want to be able to scale up the number of symbolic tasks that can actually be executed. And we have a work that is called Concept to Robot that I'm going to talk about next. And so just remembering again, the three principles that I mentioned are important. This particular work really tries to find abstractions or ground abstractions, this time not of the propositions between symbols, but this time really in terms of the actions that are being executed. And we want to enable this by really doing learning from demonstrations. And so in this last part of the talk, I want to talk about how we endow a robot with the ability to acquire manipulation concepts. These manipulation concepts can be seen as mental representations or abstractions of verbs in a sentence. And so given an initial scene image, when we send various instructions such as put something behind something or put something into something, we want our robot to generate motion trajectories to accomplish these specific tasks. And so to achieve this goal, we construct an embedding space that associates task instructions and scene images with motion trajectories. And so constructing this embedding space of manipulation concept offers several benefits. First, we can specify the manipulation task with language instructions instead of goal images. And describing a task with natural language is much simpler than already providing maybe a goal image that doesn't also potentially capture everything. So second, we can obtain a multitask policy to represent diverse manipulation skills such as open something or close something. And third, by training on a diverse set of manipulation skills, our policy can generalize to novel but similar instructions as well. And so how do we train the robot to output trajectories to accomplish this task? We use learning from visual demonstration, and this allows us to avoid reward engineering or kinesthetic teaching or teleoperation, which are often time-consuming and tedious and difficult to scale up to a large number of tasks. So again, what we make use of here is this nice data set called 20 billion something something for getting actually the visual demonstration. And as I already explained, it contains around 200K video clips and 174 different actions. And each video clip is annotated with a task description, such as putting something on a surface or moving something up. And so the challenge, though, with learning from these demonstrations is that there is a large domain gap between the human demonstration. And in this particular work, we use simulation in this particular robot simulation. And so take close something as an example. In the left, we see 4 examples of closing something, but they're really quite different from the robot simulation. And so we need a learning from demonstration method that can handle all these different backgrounds, different viewpoints, different objects, and so on. And we address this large domain gap by using a video activity classifier to evaluate robot trajectories as shown in a video. the video action classifier is trained to classify the action labels of each video clip in the 20 billion something something data set. And we use this learned classifier trained on human videos to also score robot videos. And this score represents how confident the video classifier estimates the robot video belongs to the corresponding action label, so that the robot actually executes this action. And here's a brief overview of the whole learning from demonstration pipeline. First, we send language instruction and initial scene images input to our model by concatenating their features to provide a semantic context. And as you can see here, we use pre-trained models, so for example, BERT for processing the language instruction and ResNet for the image. And then a policy generation network outputs a motion trajectory that is, in our case, specified as a goalpost and a series of forces to perturb the otherwise straight line trajectory. So it's not a feedback policy, as in many other works. And so next, during training, we execute this entire motion trajectory open loop, in our case in simulation here, and render it to get a video. And this video is sent to the action classifier to get a score, which is used as a reward. And then we run a reinforcement learning algorithm to update the parameters of the motion trajectory to maximize this reward. So the 20 billion something something data set contains 174 different action classes, and we selected actually 78 of those which are suitable for robot simulation. So for example, ripping a paper is not simulatable in PyBullets, so we use these 78 different tasks that actually are. And so we set up simulation environments in PyBullet, as I said, and for each task, we train one policy using this pipeline that I just showed you. And here are some examples of these 78 different tasks. This is the task of closing something. And so note that the testing of the policy is done on randomly generated initial object poses. And so here's another example for tilt something with something on it so that it falls. Again, it also starts from different initial conditions. And so for now, we have trained 78 different single task expert policies, each of which outputs motion trajectories to accomplish one specific task. But remember, our ultimate goal was to construct this unified model, so one policy, to represent a diverse set of manipulation skills. And so we formulate this task as a multitask learning problem. And we train this multitask policy by running behavior cloning on the previously learned single task expert trajectories. So now for the single task expert, we suddenly have actually access to the state of the robot, which we didn't have in the videos of the humans. And so now we can basically use behavior cloning on the single task expert to get this multitask policy. So the result is a unified model that can take in various task instructions and scene images as input and output trajectories for these 78 different tasks. And here again, like some examples of how this actually looks like for some of these 78 different tasks. When you put in a start image and a particular, and give it a particular instruction. Here are some more examples for other tasks. And we also qualitatively at least showed that there's some generalization if you even feed in some similar instructions to those that the model was trained on, and the robot or the policy still outputs a trajectory that makes some sense. Yeah, so just to summarize this last part, that was called concept to robot. The main idea here was to learn an embedding space for manipulation concepts that are indexed by natural language instructions. And the algorithmic contribution was an imitation learning from human video demonstration framework that uses an activity classifier to provide the reward. And the result, as you saw, was a multitask policy that can execute 78 different tasks as indexed by this natural language instruction. Yeah, so just to summarize this talk, I'm basically at the end, I basically showed you how we're slowly but certainly putting together that kind of system for a robot performing these long horizon tasks. And I showed you at the very beginning an object-centric TAMP framework that could deal with dynamic scenes. where we used a model-based tracker to basically provide it with visual feedback. Then I talked about how we can also implement closed loop task planning by using a smart way to basically use weak labels on videos to get like predicate classifiers so that you can do this reactive task planning. And as the last thing, I showed you how we can further increase the number of low-level manipulation skills that can actually be sequenced by this task in motion planner. So these were with these 3 different example projects, and I hope I also showed you a little bit how each of these is based on maybe a subset of these 3 principles to implement them. So thank you so much for the invitation and for your attention. And thank you, of course, to my students and the funding sources.
Well, thanks a lot, Jeannette, for the wonderful talk. So thank you for coming.
Thank you.
Now we have time for a few questions. So I see Rachel, you raised your hand.
Hey, Jeannette. I have a question about the second work, the grounding predicates. You showed the really neat example of the breaking the toothpick.
Yes.
And one of the predicates, and maybe this is just because not all the predicates were shown because there's like a ton of them, that one of them is that the hand needs to be touching the toothpick to break it in its way, which is necessary but not sufficient. There's like a complex style of grasp that needs to be on the toothpick in order to be able to break it that way. And I'm wondering how that kind of kinematic relation is captured when learning predicates like this.
Yeah, I think it's not captured. So, that's, I guess, the trade-off you have to deal with when you implement abstractions like this, right? So if you, for example, want to do task planning on the level of the context and maybe a particular manipulation printers that really does this kind of leverage, right, that you see here for this breaking, then I think your symbols basically have to be defined differently. Right? So I think this is really a question of what level you pick for this planning domain. Really, is this a satisfying answer? So basically, we have not implemented that kind of things, right? But I'm thinking one way maybe how I would go about it, or that comes to my mind immediately, is to say, what about defining even lower level primitives that are thinking more about these kinds of primitives that are on the level of contact and how to apply context to these different things.
Cool. So I think Richard.
Hi. Yeah. So I wanted to ask about the concept to robots. So were you training on these real something to something videos and just like using a zero shot in all the simulated environment?
A zero shot to simulate the environment, you said?
No, because you were using the classifier that was trained on real world videos to provide scores in simulation.
Yeah.
Yeah. So was this done with no like fine tuning on simulation? Like it just.
Yeah, I mean, it's reinforcement learning. So it's basically running many different trials. I don't know the number right now of how many, but it's not zero shot or mini shot or whatever. It's like million shot or something like that.
The scoring function itself, you're updating the weights of, I guess, Bert and ResNet, or at least.
Oh, no. Yeah, okay. So Bert and ResNet, we keep static, right? There's no gradients flowing to update these things. So we only train this policy network, this in the middle. That's the only thing we train. Yeah, this is maybe a bit confusing. I see here now that the classifier goes back to this entire network, but we are only training the policy generation network.
The classifier is like a learned reward function, right?
Basically, yeah. So this classifier is basically something we took from related work, that proposed an activity classifier on this, evaluated on the 20 billion something classifier, and we just used that. Maybe we retrained it, maybe we used the weights that they provided, And then we use that as a learned reward function, exactly.
Oh, I see. So yeah, I just thought it was curious because it would have to like sort of, it would have to recognize that like the robot arm is the same as the human arm. Maybe that's not that hard because it's something that's moving. Is that what's?
Yeah. So yeah, that's actually a very good question. So I have to say that the introspection on what is actually learned is we haven't done that, right? But essentially, this action classifier. One thing to remember is that it really scores the entire video. And it is trained on many different videos for closing, for example. And so it really, in order to unify all of these different little videos of closing something, we think that it really has to abstract away from appearance, and it has to look at the visual dynamics. And so in the robot simulation, although the appearance is very different from the human videos, the dynamics of this task closing something, they may be very similar to what was visible in the in the human videos as well. And that's why we think it actually can bridge this domain gap.
I see. Really interesting. Yeah.
Yep. So I think we have one question. Jeannette, do you have time, or do you have to maybe leave?
I have time for one more question, but then I have to leave to the next meeting, and I hope I can talk more to those people who are coming to the individual meetings later.
Okay, so Isaiah.
Hi, Jeannette. Thanks for the awesome talk. That was really cool. I'll try to keep it quick. I was curious why you chose to train many different policies in the reinforcement learning loop than a single monolithic goal condition policy, if your goal was to produce that at the end.
Right.
You said you wanted to have some sort of manipulation concept, network.
Right. So yeah, so you could think that maybe, let me go to that particular slide here, right? So you could think like, why don't you just train this entire multitask policy using this classifier, right? And I think maybe you could do that, but it's going to take so much longer. So this was much easier to train. It was much easier to train single task expert first, and then have access to the robot state from the single task expert, since it's executed in simulation, and then use behavior cloning for the multitask learning. It was just much easier to learn that. And yeah, that's really the only reason. It's more like a
okay, because you could, for example,
approach.
parallelize the training of all the different tasks.
For example, exactly, you can parallelize that. Yeah.
One other quick little thing on the second contribution, what happens if there are multiple objects of the same class?
Yeah, that's a very good question. So one of the things that is still missing here is, so for example, for some of these tasks, right, there are multiple objects in the scene, but we have really only trained the single task expert on one of these scenes, right? And so what is really, I think there's actually really interesting work at Coal coming out. I forgot the name. I forgot actually the name of the paper. That this particular paper also looks at the object level, and so we haven't really done that here, right? That we exploited, for example, in this 20 billion something data set, this next level of annotation, which actually replaces the something with the object, and so we haven't really looked at this on how to maybe replace the objects in the scene and then still train on this, right? So this is kind of future work, or maybe this Call paper, I think is from Lucas Manueli, and maybe Dieter Fox was using CLIP. So I thought this was really interesting coming out this year.
Great, thanks so much.
Well, thanks a lot, Jeannette, for taking the time, and thanks everyone for coming.